Because I'm behind. I'm usually not behind.
Well, it's hard to be behind.
What's that?
How are you behind?
Well, because we have a kind of in stone, pretty much, a date for your next unit exam set. Yeah, so we have that to work with. It's funny, because did you guys see that, not funny, but, so this is part 6. If you look at part 5, the title is Simple Stoichiometry. And sometimes, you know, that's a tough sort of problem to get past for some students. So there's nothing simple about it, right? So this is stoichiometric calculations, but this is looking at identifying the reactant. Now that's the stuff you start with. That's in limited supply. So limited supply stoichiometric calculations is generally what it's called. And we're going to start out not with a chemical reaction, but with making sandwiches. Okay? So basically, usually you have a couple of ingredients, a couple of reactants, and one of them you're going to run out of first, and that's going to be your short chain. In the lab that you guys did with copper, copper was your limited reactant, and I was hoping you would kind of see, with regard to the nitric acid anyway, you had plenty of nitric acid and you didn't have as much copper as you probably needed to. So I say you need to identify the reactant that's there in limited supply. The opposite of limited supply is an excess, okay? So if you had 3 reactants, one would be in limited supply, probably, and the other 2 would be in excess. Whatever's in limited supply, that's how you're going to do your stoichiometric calculation, because that's your short chain. You can't pick something that's in excess and see how much product you can produce, because you're going to run out of the things in limited supply. Okay, that's kind of the idea of this sort of calculation. Okay. So I mentioned we're going to start with making sandwiches first. Okay. So I want you to look at this, and we'll go ahead and we're at 10 points. I'm going to pass this around, and you guys are going to answer these. So the first, I'm going to pick on 4 people here. So, I know. And actually, you probably don't need your calculator for this one, but notice we're just making sandwiches. And we're making simple sandwiches. Sandwiches that have bread on the outside and a piece of ham in the middle. So it goes like this. Notice that we know how you make a sandwich, and the kind of the relationship between the bread, the ham, and what you get is up at the top there. If you know that you have 20 slices of bread and 7 slices of ham, so what are you going to run out of first? What is the limit? Oh. Sorry. Psych. You're fine. It is this one. Make it green. Go green. There. Okay. So you're going to run out of ham first. I agree. Is everybody kind of thinking that too? Okay, and then what are you going to have left over? That's the excess one, so write that next to the ham. This thing's not going anywhere. Okay, good. Very good. And then how many sandwiches can we make based upon the ingredients we have? 7. Are we all good with that? Notice by coincidence that the ham was limited, and we have 7 slices of ham, and we're going to make 7 sandwiches. For every sandwich we make needs 1 slice of ham. That's all good. All right, next one. How many slices of bread will we use to make our 7 sandwiches? Perfect. All right. And over to Tyree. Based upon all that, if we use 14 slices of bread, how many slices of bread are we going to have left over? 6. Okay, you guys have just done a limited supply calculation. Although it wasn't with chemicals, and I'll be back. It wasn't with chemicals. Okay, so let's bump it up to something a little more interesting. So I'm just going to kind of talk through, before we kind of switch to chemicals, talk through what we kind of did. So from the recipe of the balanced equation, okay, and you're going to see me use these terms. You see the term need? Okay, I like using that term. What do you need? We get that from the recipe. Okay, we got the 2 slices of bread for every 1 slice of ham. Those are like kind of what? Stoichiometric coefficients, aren't they? What you need. So what we have, again, we still go with the bread to ham, was 20 to 7. That's what we have. We can take 20 and divide by 7. We can actually get a number, 2.86 slices of bread per 1 slice of ham is what we have. Now, you guys didn't think all through that. You didn't come with 2.86. Well, actually, he might have. Jason might have. Mr. Rainman. He's funny. He does calculations in his head. But my point is, can you see where I'm going to have you compare, like this says, I'm going to have you compare what you need according to the recipe or the coefficients versus what you have. So can you see where you have more slices of bread than you need? Does that make sense? 2.86 is more than 2. You have more slices of bread than you need. Sometimes I chant that to myself. I have more slices of bread than I need. So bread must be in excess, okay? And the other reactant, which is ham, must be limited. So that's kind of how that goes. There's other ways to work this, but I kind of usually go with the have and the need approach. Okay. So you guys correctly, intuitively came up with the right answer. You know? You guys will do great. So notice that one of you guys said, if we're going to run out of ham first, okay, we are going to run out of ham first, and the number of sandwich weeks we can knock out are 7. 7 is the amount of ham we have, okay, and does that middle thing kind of look like, hopefully, a stoichiometric ratio? Like, how could you take something wonderful like sandwich making and turn it into something evil? Okay. Okay. So this is like the need ratio, I guess you could call it need ratio. Okay. That's from the balanced equation. And what you start out with, this is what you have, right? I could put that over 1, and slices of ham cancel. We're left with sandwiches. Notice that anytime we do a stoichiometric calculation, if this is stoichiometric calculation, we always use the reactant that's in limited supply. On your homework that's going to be due Wednesday, on the front end, you're going to see which one you're going to run out of first, and then you're going to apply it to calculate a stoichiometric calculation. It's kind of like a 2-step approach. Guessing does not count. As you probably already figured. Okay, got 50-50 chance, right? Okay, so we can use the, again, limited supply ingredient to see how many slices of bread we'll use. Again, kind of that ratio thing came from the recipe. That ratio thing came from the coefficients of the balanced equation. We know we use 2 slices of bread for every 1 slice of ham. 2 bread, 1 ham. Slices of ham cancel. We're left with slices of bread that we're going to use. So that last calculation, it's really kind of standard to find out when your reaction's all done, how much of the ingredient or reactant in excess do you have left. It's very common. Your boss might ask for that. Okay. So you started with 20. Based upon stoichiometry, you know that you're going to use 14 slices of bread. So 20 minus 14 gave you 6 slices remaining. It's a classic. Okay. So this little thing in the box down here is reminding you that when you're faced with, and you will be, problems that say, how much of the excess reactant do you have remaining? Notice we could only get to that number by calculating how much we use up and then doing a subtraction. That's it. And we calculate, what's that? Oh, we calculate how much we use up from a stoichiometric calculation based upon the limited reactant. So I'm not going to really belabor this one too much, but it's a figure from your textbook. Over here on the right, it kind of shows you what the goal is to go ahead and prepare little packets. And each packet needs to have a cover sheet. It needs to have 1 sheet of instruction, 2 data sheets, and 4 sheets of graph paper, so little packets. And then kind of like these are reactants, okay? So you're going to assemble these things to make your packets. And what you would find out is that, looks like the one you're going to run out of first actually is the, see that graph paper is the limiting reactant or ingredient. Okay. So let's look at a real reaction. This is sometimes called the Haber reaction, making ammonia from nitrogen and hydrogen. It's balanced. Okay, you're going to need it balanced. And let's see, did I think I did. Okay, let's watch this little, I don't think there's any sound to it. Okay, it's simply saying the have amounts are 6 and 12. 6 molecules of nitrogen, 12 molecules of hydrogen. And you're going to see the little dance and see what's left over. Okay, so the 3 sets of 3 atoms are NH3. Okay, and it looks like what we have left over is N2. So I put together this kind of, let's see if this works for us, kind of a look at that example using the kind of have and need approach. Okay. So in the given information then, it said that we have, it said that we have, let's see if it goes that. So you saw nitrogen's left over. But what you're going to see me do next is come up with a have ratio. Okay. We have 12 molecules of hydrogen for every 6 molecules, 12 molecules of hydrogen for every 6 molecules of nitrogen. You divide that out and you get a 2 to 1. What you have is 2 molecules of hydrogen for every 1 molecule of nitrogen. And then my need ratio, just kind of like we did with the ham sandwiches, it's going to come from the balanced chemical equation. So the coefficient in front of the hydrogen is 3. The coefficient in front of the nitrogen is 1. So what we need is 3 to 1. So can you see where we need more hydrogen than we have? We need 3 to 1. We have 2 to 1. Okay, so if we need more hydrogen than we have, hydrogen is in limited supply. Those big blue things you saw in the animation, nitrogen, that was in excess. Okay. So that's kind of, and there is another approach to working these, but you have to identify what you're going to run out of first. Okay. So it's a 2. I hope you're kind of getting this. It's a 2-step. Unless they say that they give you the limited reactant. Unless they give you the limited reactant, you have to figure out which one you're going to run out first. Step 1. Step 2 is to do the calculations you've been doing. Stoichiometric calculation.
Where did you get the 6 and 12 molecules from?
That was the given. That was kind of the random. That was specific to the problem. That was kind of in the paragraph. Yep. That could have been anything. They just said that's what your cupboard has.
Sorry, you didn't get
There you go.
Okay, so this is where I'm going to kind of turn it loose to you guys again. We're 10 points, remember? And this is very similar to what we did with the ham sandwiches, okay? Except it's, instead of bread and ham, it's nitrogen and hydrogen. Instead of making sandwiches, it's making ammonia, okay? Yeah, even better. So we're going to do step number 1. What are we going to run out of first? Notice that we have the given amount. So I'll just kind of start to set the stage. And then, like I said, I'm going to kind of pass this around. But what I usually do is take those masses and put them under the thing, because otherwise I get confused. So 7.20 grams of nitrogen. Wait, 72, well, you know what I mean. 72.0 grams of nitrogen and 22.0 grams of hydrogen. Okay? Otherwise, like I said, I get confused. Now, when I pass this around on the next slide, you can see we got to turn those masses into moles, because the half ratio has to be moles to moles. It can't be grams to grams. Okay, so that's going to be our first step. And then we're going to compare the half moles to the need moles, and of course the need is a 3 to 1, isn't it? Okay. And then step number 2, we're going to see, I'll talk you through it, but basically we're going to see, remember how I said how much bread is left? We're going to see how much of the excess reactant is left. And then the last one, we're going to see, when all is said and done, not how many sandwiches, but what mass of NH3 can we produce. So to just kind of talk you through it, this time I did go ahead and put this in writing mode. I do have, you calculate the molar masses, because you might not know what you're supposed to do. Oh, Mrs. Snipes, what? Oh, good, thanks. They got the molar masses. Okay. So you have the molar masses. So now we need to use those molar masses to knock out the moles of everything. So the moles of the reactants, I guess. So what do you think, Kelsey? Can you get me the moles of N2? Put you in writing mode. Whatever. I'm trying to hit that pencil. Okay. From a given mass, what's the moles of N2? So you start with the mass of N2.
Isn't that the mass?
That's the molar mass, and you're going to use this 72.0.
Oh, okay.
And to go, you can either erase it. Yeah, there's an eraser. So go ahead. Cool. And then we'll go back to the writing utensil.
Okay. When do I do this? The 28.
And you want to be left with, yeah. Perfect.
I mean, over 1 mole.
Yep. And is this where I hand it over so Andrew writes the equals? Or what did we do last time? We don't have to do it all the same. So how many sig figs are you going to do, Andrew? Yep. Burp. And the tube, you've got moles of hydrogen. Awesome. That's nitrogen, though. I threw you off.
What?
Okay.
Oh, nitrogen, what the heck?
Just turn that into a...
I'll just do this.
Perfect. Thank you. You got it. He was going to do this. Okay. So how about set up going to moles of hydrogen and knock out moles of hydrogen?
Oh, follow, make sure. How do you get to right?
Top on.
Oh, there it goes. Hmm?
Perfect.
Such a struggle. Poor thing.
No, choked him out.
How many sig figs you gonna get us, Chelsea?
3? No?
Yes.
Oh. So, is it going to be 11 moles of H2?
And Alexis, we're gonna be back to you to give you the half ratio of moles of H2 to moles of nitrogen. Thank you. Any questions about this? Just let me go on to the next
Do I need
slide.
to, like, divide it?
Yeah, show how you're doing it. Let's see. There. So I kind of want you to write it down there. See where it says have. Perfect. Oops, I need to get you in writing mode. Sorry.
Okay.
Let's see. Right. Right, darn you. Fat fingers. Okay.
So, it's H2 over N2?
Yeah.
Okay.
Yeah, you could go either H2 over N2, and the reason I usually choose whatever's going to give me a number greater than 1, looking at the coefficients of 3 and 1. If I put 3 over 1, I'm going to get 3. I could go 1 over 3, but then I'd get the... Very good. And you could just leave it 4.28.
Okay.
Or you could go ahead and say 4.28 moles of H2 per moles of N2. Either way. What you think, Heather? So you got from the stoichiometry, what we need. So like up here, can you say what we need, the moles of H2 to moles of N2 that we need from the balance equation? And then Matthew, you get the coup de grace. And guessing doesn't count. That's it. Yeah. 3 divided by 1 is 3. Okay. So based upon the ratio of what we have versus what we need, what can you say about hydrogen? So with regard to hydrogen, we have 4.28 and we need 3. So you can scratch this. So just go ahead in general. What would you say with regard to hydrogen? Is hydrogen in excess, or is hydrogen, we're going to run out of hydrogen first?
Hydrogen would be in excess.
Very good.
Because you almost have enough for 4, while you don't even have enough for 3 for N2.
Right, I agree. So just write H2 in excess. I know it sounds a little redundant, Jason. I didn't call the wrong people the wrong names. But if you could, then what's in limited supply? You just say 8 and 2 limited. Perfect. Yep. Bless you. I'm liking that. So we did the first question then. The first question was which one's in limited supply. And so all of your stoichiometric calculations are going to be based upon nitrogen, N2. So that was the first one. The second one was, all right, how much hydrogen are we going to have after we use up all of the nitrogen? Because we know hydrogen is going to be limited. Okay. So it looks something like this. Okay? So you can do the whole thing if you want to, but this is kind of like the calculations you guys were doing for regular stoichiometric calculations. So you're going to start with the moles of nitrogen and get ultimately to the mass of hydrogen. Oops, sorry. Needs to be green.
Start with the mass of. What is it?
Hydrogen. Oh, yeah, mass of nitrogen. So, what was that? 22 grams?
For the N2, it'd be.
N2.
It'd be 28.02, I think.
Okay. Well, that's the molar mass.
Okay.
You need to go with the original problem said, yeah, 72.0 grams N2.
72.0
0 grams
of O2.
N2, because that's your limited over 1. And now you're going to get to moles.
So I would need
And you were right with
the 28.
Yeah. Mm-hmm.
28.02, and that's what grams of.
Per grams nitrogen.
Do I need a 2 there?
Yeah.
That's over 1 mole.
Uh-huh. Mole.
N2.
Yep. And I'm going to have you then do the ratio from the balanced equation
Okay.
to get to moles of hydrogen now.
Okay. Shift the balance.
And it's down there at the bottom.
So I would need 1 N2 on the bottom.
Right.
And
1
then
mole.
3 H2 on the top.
Right. 1 mole and 2 on the bottom. See what he's doing? Yep. He's basically doing a stoichiometric calculation
Moles.
based upon a limited supply reactant. Perfect. And then one more term, we'll have you knock it out here. One more term to get from moles of hydrogen to grams of hydrogen. Use its molar mass.
So I would need the H2 on the bottom,
Right?
right? And
Mole H2 on the bottom.
moles H2.
Grams H2 on the top.
How would I do that?
So it's the molar mass again. So I saw you look at the decimal number for hydrogen.
Mhm.
So
That's
it's going to be 2.016 grams H2.
2 points.
No, that goes on top.
Does it? Oh,
Mhm.
shoot. Where's the eraser at? That one?
Yep. And then the writing utensil.
Oh, shoot. Yeah, now I do. I erased all my work.
Actually, he did. Let's see. No? Yep.
Yeah, I erased it all.
Oh, no, I got an idea. So it's right here. Let's go back to, does that look familiar?
Yes, it does.
Bring her up. Look at him go.
I'm doing it quick.
Mm-hmm. Yep, keep going. All right. So one last term.
So that was the 2 point. Oh, I'm still on.
Yeah.
Fourth time's a charm.
Yeah.
No,
Heck
this
yeah.
is a third, but I'll go for another one.
Okay, so it's already green, so you're good to go.
You sure?
Yep.
No, it's still on eraser.
Oh, okay, yep.
Oh, there we go. Okay.
Yay!
6. Yeah. Tell me about it.
Factor label rocks. Okay.
And then, are you sure?
Yeah.
What do I need on the bottom? Just 1?
1 mole H2. So what you have is the molar mass of H2.
Just 2.
Perfect.
That was something.
Thank you. You did well. What do you think, Kelsey? How many stick figures you around to?
3. Is it 15.5?
Sounds good to me. And units? Perfect. Alrighty then. We still didn't answer question 2 because Andrew, now we need to say, if that's how much we're going to use up, how much do we have left? It's like a lot of work to, let's see, I need to get you back to this. There's all you did. Oh, sorry. Okay, so if you could go ahead and say how much we have left over. Am I on anything that's going to break? Wait, oh yeah, it's green. Well, your writing got really neat there, Tyree.
I know. It's crazy.
Any questions? Any answer?
Is there an extra step in the one that I did compared to the one that's written up in it?
Yeah, you went, they piggybacked on, earlier in the notes, you had moles of N2. Instead of 2.60, actually, really 2.57, which is fine. You could have done that. I just kind of went back to, thank you. Very good. Any questions? So that's number 2. Arr. So if you guys don't mind, bless you, and even if you do mind, answer the last question, that would be great. Did it go backwards? This one. This is question number 3. What mass of ammonia can be produced? Bless you.
Bless your soul.
Okay. So,
You got it, David. Knock it out.
well, you'll be fine, David. So which reactant is in limited supply?
The nitrogen.
Nitrogen, yep. And so that's how you're going to work this problem.
Okay.
So you can either do that 2.57 moles of nitrogen and knock out to grams of NH3, or you can do like I had Tyree do, the mass of nitrogen, the molar mass of nitrogen, and then that way.
What now?
So what I would do is, you told me nitrogen, so in order to know how much NH3 is produced, we have to start with the nitrogen, yeah. So what you can do is use this moles of nitrogen as your first term.
2.57.
Over 1. And then now you're going to go to moles of NH3 using this balance equation.
So
Moles of
you're
nitrogen
gonna
bottom, moles of NH3.
put 1 in. You're gonna put 3H on top and 1 in on bottom.
3H2.
No, we're not going to H2 though. We're going to NH3.
So put 3 in
It's
H3.
gonna be 2 in H2. 3. Yeah. It's gonna be 2 in H3.
How do I raise?
You can do the little hurricane looking one,
There.
or you can do that. Or you can do that. Okay, so
Okay, so 2 in H3.
moles of NH3.
You could have just okay.
Over 1 mole of N.
Yeah.
Any questions?
Yeah. Okay, now
Now get to mass of NH3, and you can use this number right here.
so it's 17 point. So
Which one did that go on the bottom?
So you want to be left with grams. So
grams
one
go-
mole goes in the bottom, and your
1 mole of
Oh.
NH3, right?
NH3, yeah.
Good job there, Dave.
And then 17.03 grams of NH3 equals, right? Or am I jumping ahead too far? That's supposed to be a 7?
Come
I don't know,
on,
you
get with
tell
the
us.
program.
Very good.
I'm terrible at this.
Any questions?
My penmanship is terrible.
That was much better.
That's good. I've seen worse. Okay. So, kind of to summarize, this is kind of answering those 3 questions. All right, so alternate approaches, and one of the things that I look for is you have to, on the front end of a limited supply reactant problem, on the front end of any stoichiometric calculation, if they don't say what's in limited supply, you have to calculate it first. Don't fall into that trap. But there's other ways to do it than just the what we have ratio versus what we need ratio. And here, these are two alternatives. Sometimes students really like this. So, for instance, you could pick, if you had two reactants like we did, okay, pick one reactant and do a quick stoichiometric calculation to see how much, if you use all that up, how much of the other one you'd need. Okay, and then if you have extra, then that must have been the limited supply. If you don't have enough, okay, then that must be, that's in excess, the one you started with. Okay, just kind of logically, whatever you do, you have to show me. And a lot of times students like this other one. This is kind of fun. So basically, you look at the product, okay, you see how much product you can get from each reactant, basically. And whichever one gives you the most product, that's the one in excess. Okay, that's kind of fun too. That requires two stoichiometric calculations. Okay, so whatever you do, you know, just kind of lay it out the front end, how you identified the limited reactant. Because only like we did, I hope you kind of get the idea that only once you say which one's your short chain, which one's limited, that's when you can go ahead and do your ordinary stoichiometric calculation that you guys handed in today. I know. Okay. So these will be due. We're going to go take a look at the next part. Just two of them. Okay. 63 and 64. So if you got that, I'm going to, and I think in order to kind of save time a little bit, I'm just going to show you what I did back at my desk with 63 and 64 to kind of, where did it go? That's not it. That's it. Okay, so here's 63. Yeah, I know, but 63, if you read it, it's basically, don't let it throw you off because it's doing the whole mole thing, which is a little less complicated than the gram thing. Okay, so the have amounts, they give you moles of the two reactants. Okay, my step number one here is to kind of go with the ratio of what you have, 4 to 3. Okay, and then down here, then when you identify the limited reactant, then you go ahead and do your real stoichiometric calculation, which is the question mark moles of NO. And these, I'll try to save as PDFs and make them available. Notice how, okay. So, but the other thing, this is the next problem. And honestly, if you want to jot down that balanced reaction, that would be good. This will help. Squiggly line, LOL. So they give it in words, the calcium hydroxide reacting with water to form, the calcium hydride reacting with water to form calcium hydroxide and hydrogen gas. They just give it to you in words, and it's really not fair. So when I assign this, usually students, if I don't give them the balanced equation, it makes it hard. So that in black up there, if you want to, you'll just want to make sure that you balance it first. Okay. So we're going to go ahead and take a look at, like I said, I'm going to make these available. In the meantime, let's take a look at percent. Let's take a look at percent yields. Maybe. Fat fingers. Okay. As this topic, for your unit exam for this material, I look for things that aren't numbers, and this actually is not numbers. So this topic of percent yield might show up in vocabulary or short answer. Okay, so look at this before you take your test, all right? So theoretical yield, whenever you do a calculation to see how much stuff you're going to make, okay, that calculation is giving you a theoretical yield. Okay, theoretical yield is just based upon stoichiometry. What should you get? What grams should you get back? Or what moles should you get back? Okay, so you guys have been doing theoretical yields. In theory, what should you get back based on everything being optimum in the lab setting? Okay, so one of my things that makes me smile is why don't you get back what you think you should get back? Lots of reasons, right? But all of these reasons, it's kind of funny, you guys just did your copper lab. How many people got more copper than they started with? Yeah, I think everybody. So these are all reasons that actually your results will be biased low, because usually your results come in a little bit lower than they should be. So I'm going to kind of talk you through each one of these. So for instance, in Gen Chem 2, we talk about the fact that just like light takes a discrete amount of time to travel from point A to point B, okay, chemical reaction takes a discrete amount of time to go to completion. Okay, how fast it goes or how slow it goes, a reaction goes, is called the kinetics of the reaction. It's kind of fun because you actually kind of look behind the scenes of a reaction and kind of anticipate slow or fast reactions. But this is to say, let's say you're impatient and you just don't give the reaction long enough time to proceed to form products. Okay, so this is kind of showing you the R is the reactants, the P is the products. And so not so surprising, your reactants will go down and your products will increase. And along the x-axis is time. So it's kind of showing you over time. So this caption says, you know, say you were going to stop at 7 seconds. So this is 2, 4, 6, 7 seconds. Okay, say you're going to stop there. Notice that you only have, if you start with 0.2, you've got about half and half. You've got about half of your reactants left, and you've only formed half the products that you can form. If you're impatient, stop at 7 seconds. Okay. Versus if you go to 30 seconds, okay, do you have it all yet? Not quite. Okay, at 30 seconds, you still have a little bit of reactant left, and you have a little bit of product to go. So kinetics. The other one is you just can't win because actually, instead of your reaction occurring in one direction, some of you are kind of familiar with this, and again, we kind of hit this in Gen Chem 2. I told you that chemical reactions are written from left to right, R to P, like that. Okay, but there are definitely some important chemical reactions that go from products. You can kind of think of it as break back down to form reactants. So actually I have a two-way arrow up there. And we call that in chemical equilibrium, or equilibrium. It goes back and forth. You're like, dude, I'm not ever going to get 100% products. Okay, it's just kind of how it's set up. The next one is, this is showing you an example of a chemical equilibrium. The next one, actually ran into this when you guys took that magnesium ribbon and quilled it up into your crucible, and you heated it up, and you hoped that oxygen combined with it to make magnesium oxide. Well, in your write-up it said that actually in some cases nitrogen will combine with those cute little magnesium atoms and make magnesium nitride. That's an unwanted side reaction. Okay? So it's just inherent in the experiment. But again, a reason you wouldn't get all the magnesium oxide you thought you could get. So physical losses, not to be confused with oops. Okay, oops would be experimental error. Okay, but physical losses are again are inherent to kind of the way the experiment's set up. A lot of times there's transfer issues. Okay. So here's the deal. Oftentimes, especially I think of pharmaceuticals as wanting to be ultra pure. Okay. And there's ways to take something you think is pure and purify it some more, and purify it some more. You know, change your techniques up, purify it some more. In organic chemistry, if you stay in chemistry, this is general chemistry. Organic chemistry will be like your next stop. And they do a lot of kind of playing in the lab with purifying stuff. Okay, but you lose, every time you purify, you lose a little bit. So it's kind of a trade-off. That's why your aspirin costs so much. No, aspirin doesn't cost so much. Okay, so isn't that adorable? Yay! So to get on the nose what you think you should get, okay, all of the stars or planets need to align. Okay, all of your limited supply reactant needs to go to form products, okay? No side reactions, and you need to be able to recover what was formed. So it's kind of, yeah, can kind of be a challenge. So the oops error, the gross error, that would be, and it happens, like if you accidentally spill something. Another oops error is if you like record something wrong on from the balances, or you read a beaker wrong, or read a volume wrong. So those are all what we call gross errors. Gross errors are in general is what we can say as they are avoidable. And it might be on here already. Okay. Okay. So you guys are going to do this calculation for your copper lab when you go to turn in your write-up on Thursday this week. Okay. Basically, a percent yield is kind of a straightforward calculation. In the top, you put, sometimes I put that as experimental yield or actual yield. And in the bottom, you put your theoretical yield, what you got based upon a stoichiometric calculation. So this is experimental yield. Okay, and this theoretical yield, this is from Stoich. I bet you guys know what I mean when I say Stoich calculations. Okay. Notice it can be either in grams to grams or moles to moles. So just one quick kind of problem. This is, again, kind of like what you did in the lab. Let's say we ran this and actually, do you remember we had said based upon like 1.25 grams of Cl2 and sufficient P4, or the other way around? Yeah, there you go. We said that in theory, you should get 1.61 grams of product. Okay, so that is your theoretical. That's going to go on the bottom here in a minute. Oh, sorry. This is your theoretical. And it's always got to be the product, right? And this was your actual. Okay, so on the next slide, basically, it's just a ratio of those two. Okay. Round to 3 sig figs, 67.1%. Yeah. What are you going to do? There could be all sorts of reasons for that. It's funny because I think out in industry, they're willing to kind of cut their losses and they understand the chemistry and the nature of things. Okay. So, assignment slide. Dun, dun, dun. Notice I added 69. So, let's see. 1, 2, 3, 4, 5. 5 problems. I'll have my phone handy. I should be in the office Wednesday. I'm usually there by 9:30 if you have any questions. And I'll put screenshots out there of these two. But I don't think there's not an issue with balancing the equations. Or I'll show them to you for those of you who can afford the time. So this is the first one. Okay. It's not too bad. Notice that you don't have to say which one's in excess. That's kind of fun. The next one, also not too bad. One reactant breaking down to form 2 products. 69 is kind of back to what we did with identifying a limited reactant. Oh, yeah, I will push this out there because you'll need 69 is kind of like that one where you have to take from the paragraph what the reaction is and balance it. Okay, very good.